Good morning, class. Today we are going to start where we left off on the Part 5 atmosphere notes, and we're going to start with the trade winds. So trade winds are one of the global wind belts, and they are located closest to the equator. And you can see here the direction that they are blowing in, and you can also see the way that they're curving. This curve is due to the Coriolis effect. Remember that the Earth is spinning counterclockwise, and therefore when the winds start to blow in the region of the higher air pressure, which is closer to the 30 degrees north compared to the lower air pressure at the equator, or it could be at the 30 degrees south compared to the lower pressure at the equator. Either way, when they start to blow and move towards the equator, they get curved because of the Earth's rotation. And again, that's called the Coriolis effect. So these blow from the 30-degree latitude, either north or south, and they blow towards the equator, and they curve because of the Coriolis effect. Moving on, we're going to look at the prevailing westerlies a little bit more closely. The prevailing westerlies are located between the 30 degrees latitude and the 60 degrees latitude line, and that is both above and below the equator. These are different from the other two types of global wind belts. So again, we have the trade winds down here. We have the polar easterlies up here, and so what happens is both of those, the high pressure is located away from the equator, the low pressure is located on the equator, and therefore they're moving towards. Here what's happening is the high pressure is located at the pole, and then the low pressure is located at the 30 degrees line, and so the air is moving towards the equator here. But these are the opposite. They kind of lie in between, and the high pressure is actually here compared to the lower pressure here. And we'll kind of talk a little bit more about that in class. But we do get winds that move in from the west, which is called the why they're called the westerlies, to the east, and that's why living in the United States we get affected by these global winds the most, and our weather moves from west to east due to this global wind belt. Next we have the polar easterlies. We kind of just talked about these in the last slide, so I'll just kind of review. These are located at the very far south part of Earth, or the very northern part of Earth. And these again move from the east to the west, so that's why they are called the easterlies. These move similar to the trade winds. And moving on, we have now to talk about the calm parts, because the whole time we've been talking, the last 5 minutes or so, have been about the winds, the global wind belts, the winds that cover large distances and can have pretty strong winds that influence a lot of weather and drive the climate zones. So we talked about the trade winds, the westerlies, and the easterlies. Again, down here, the trade winds, the westerlies, and the easterlies. And so now let's talk about these areas where there is no wind. One area is called the doldrums. The doldrum is located right at the equator. And what happens is, if you remember, this is the lowest pressure on Earth due to a lot of warm tropical weather. And so the air pressure is very low. And because of that, the air here will rise because of the high temperature. So instead of blowing horizontally, the wind is rising from the Earth's surface at the doldrums. Sometimes this affects boats because especially if they are being navigated somewhat by the wind patterns. There is no horizontal movement of air here, so that's why it's called the doldrums. All right, and then we have the horse latitudes, which is located at 30 degrees north and 30 degrees south of the equator. And these are also an area where there's no horizontal movement of air, so there's no wind. In fact, here, because it's a higher pressure of air, the air temperature is cooler, and so it's falling in these areas. So instead of rising like at the equator, it's falling. It's becoming more dense here and here. These areas are called the horse latitudes. Now, there's a reason why they named them the horse latitudes. Supposedly, this originates from the days when Spanish ships would try to cross the ocean, and they would be carrying horse that were needed. And because they would get stuck for several days, maybe weeks, in the areas of the horse latitudes where there was no horizontal wind to help move the ships, then they would have a lack of water and food. And so because of the lack of water, they had to sacrifice some of the horses. They couldn't allow the horses to drink the water because they needed the water supply. All right, so by now you should know what wind belt we live in. So if you don't, you can find North America on this map, and you can look at where it's located in north or south of the equator. You can also look at the wind direction that is happening here. So if you find North America and you find where Ohio would be around the A, then you would see that the wind is moving from the west to the east. And there's only one type of global wind belt that this happens in, and that is the prevailing westerlies. And the proof of this would be in our weather systems. Most of our weather, 90% of the time, when we watch the weather station, we're looking at the weather that comes from the west because that will be affecting us. All right, so now we need to talk about jet streams. Jet streams occur even higher up in the atmosphere than these global wind belts, and they take place in between the global wind belts. So they're like rivers of air flowing in the atmosphere, and they're very, very, very high-speed winds. They can move up to 200 to 400 kilometers an hour. They do generally move west to east, similar to the prevailing westerlies. And what's interesting is there are two jet streams. One will be moving at the top of the westerly, near the 30-degree north and south of the equator, and then one will be moving at the 60 degrees north and south of the equator, which is beneath the westerlies. So these jet streams have a huge impact on our weather and climate, as I think you might have noticed in the middle of November. The jet stream was pushed upward in the Pacific Ocean, which then caused it kind of shift way down over the United States. And so that cold air from the polar region north of us was shifted downward, and therefore we got more snow because of all the moisture in the air at the time, and because the temperatures dropped, then that moisture turned into precipitation. All right, so how many? There are two jet streams, again, like I was saying. One is located north of the westerlies, and that's called the polar jet stream. Makes sense, right? And then there is the subtropical jet stream, shown with the red arrows, both north and south of the equator, and that represents a warmer jet stream. So why do these occur? These occur based on temperature differences. And don't get that confused with what causes global winds. Global winds are caused by air pressure differences, and strictly the jet streams are caused by temperature differences. So way up high in the atmosphere, where the convection currents meet, these global wind convection currents, right above those, you have warmer air rising, you have cooler air sinking, and so because of that, you have a fast-moving jet stream that shoots through there. So here we're going to break that down again. Factors that affect the jet stream: temperature. Factors that affect global warming: air pressure, differences in air pressure. Factors that affect local winds is more about the differences about how water and land heat up and cool off differently. Okay, so the jet streams kind of form a border. They form a border between the three different global winds in each hemisphere of Earth, and they have, if the temperature differences are greater, then there will be more speed. If the temperature differences between the two convection currents that are colliding are similar, then they have less speed. All right, so seasons of the year. These are more active, and this would make sense, in the winter time. Why? Well, because in the winter time you're going to have greater differences between the temperatures of the convection currents that are meeting. And so they would be moving more fast. That doesn't make sense. They were moving faster due to the major temperature differences. Thank you very much. Have a good day.